Okay, so um, I'm covering properties of limits, and what I'm doing here is more, I mean, we're talking about limits, and the application assignment is dealing with some of the basic limits by finding limits with like a table or with graphs. And the very last problem you can, I recommend actually kind of looking at a graph for that, or I do have a video on doing it algebraically. I know most of you do have to go on to calculus, and so the first week of calculus is limits. And so I figured what I'm going to do is kind of talk about the stuff that you'll be learning in calculus, so that way you kind of already got, that first week some information there, and so that way you're just kind of better prepared. And it helps reinforce what we're doing with limits, as far as like graphing and tables and that sort of thing. So first, the concept of the limit is a very important concept, especially when you're going into calculus. So we've actually done limits in algebra. When you have college algebra, you have limits when you're looking at end behavior of a polynomial, and then when you're looking at asymptotes of a rational function. And when we're thinking of limits in algebra, we're basically saying, as I go to this x value, what is happening to my y value? And with end behavior, you're looking at, as my x is getting really, really small or really, really big, going to positive or negative infinity, what's happening to the y value? And so that's usually where we say it goes up or it goes down. And then with asymptotes, the horizontal asymptote is a limit, basically, when you're looking at positive or negative infinity. And then we have the vertical asymptotes being limits when you're looking as your x and y are going, or as your x is going towards a vertical asymptote, what is happening to your y? That's another type of limit as well. So the concept of a limit is just, as you approach something, some x value, what happens to the y? And the y may get near a number, but not actually hit that number, such as with horizontal asymptotes, we don't actually reach necessarily the horizontal asymptote. It may go towards infinity and never actually be at a single number. Like if you're looking at a vertical asymptote, at a specific value, your graph might be approaching infinity, but you don't actually have a number that you reach. So you just say, well, it's basically going up forever. And then sometimes your limit is actually a number, a specific number that you can touch and is basically existing. So there are there's different limit notation. And the basic thing is that you've got a lim, which is the abbreviation for limit. Underneath it, you have your variable, your input variable, an arrow, and then where you're approaching. So might have a number there as x is going towards 2. Or you could actually head towards infinity. So as x is going towards infinity, you might have infinity there. Then you have your function, your y that you're actually interested in the limit for, and then equals, and then whatever that number is. There are variations on that where you have an exponent of a plus or a minus, and that just means that we're looking at only on the left side or only on the right side, because if you're approaching a value, say 2, you can approach that value from the left and from the right. So you can go towards both ends. And generally, when we're asking about limits, we want to know what happens as you approach from both sides. And everything on the homework is about both sides. We're not doing any one-sided limits. We're just saying what happens as you approach from both sides. But there are types of limits where you only want to look on one particular side of the graph as you're coming from the left or maybe coming from the right. And we indicate those with plus or minus. So that's the basic notation, is you have lim, you have x, arrow, and then wherever you're going, your function, and then what it's equal to. So there are tons of properties and we'll do examples of all these, but so this is really kind of getting at the notation here. So our basic definition the most basic type of limit is that if you are having some function and you want to know the limit as x goes to some number, which we'll just call c, you just plug that number into the function. That works most of the time with most functions. If you want to know what is the limit as x goes to 2, you just plug 2 in for x, and that will be your answer. There are cases where that doesn't work, and then that's where you start learning other tricks to do. Like with a vertical asymptote, you can't actually plug that number in. So then you have to look at different options, and that's sort of where using a table comes into play, or doing a graph. If you're asking for the limit of a constant, you know, what happens as x goes to 2 when your graph is 5? It's just 5, because your value is always going to be 5. So it doesn't matter what your value for x is if you're just having a constant. The two basic functions are just the limit of x, where you just plug in the number, and then the limit of x to some exponent, like x squared, is you plug in that number and then square it. So these are really, you might think, well, what's the point of taking the limit? You're just plugging in the number. It's when you start getting into the ones where you can't plug it in that it kind of gets a little bit more important. But basically, you're just plugging your number in for x, seeing what the y is. For the 6 trig functions, the limit is what you can plug in, basically. So if you can plug in the value, you do so. So those aren't any, they're not special. They don't have any different rules. You just, if you want the limit as x goes to 2 pi of sine of x, you just plug 2 pi into your function. And the first homework assignment has a function that has sine in it. It's sine x over x. And so you can just plug those values basically into your function, because we can plug the value in for sine, you can plug values in for x. So you just literally plug those numbers in. These properties are things you can do to limits that allow you to take a really complicated function and kind of break it down into something a little bit easier. So we have b and c are just real numbers. So just numbers. N, as we have it under the power, is just a positive exponent. We have functions f and g. And we're just going to say whatever the limit of this function f is L, the other one is k, just whatever the number is when you actually find the limit at that particular value. So the scalar multiple basically means that if you have some function and you multiply it by a number, it's the same as taking the limit of the function and multiplying that limit by a number. Essentially what this means is that you can factor out constants, find your limit, and then multiply it back through. The sum or difference is basically saying that if you have a function where if things added or subtracted, you can break it apart by taking the limit of each term and then adding those results together versus taking the limit as the whole thing. The product property here is that if you've got functions that are multiplied together, you can find the limit of each factor and then multiply it. So instead of finding the limit of the whole thing, you can find the limit of the individual and multiply them together. Quotient is similar, but it's with division. So that one is handy with rational functions. Essentially, if you have a rational function, you can find the limit of the top, the limit of the bottom, and then divide your answers. And then we've got power, which is if you have some function to an exponent, you find the limit of whatever's inside the exponent, and then you can take that exponent on your answer. So what these properties of limits are basically saying is that the rules of arithmetic apply to limits. So limits behave like anything else in algebra behaves, where they add together, they multiply, they divide. Like they don't have any weird behavior. They follow the same rules of algebra. And having these properties actually kind of helps you break limits down into a smaller form, and it can make your life easier. So other properties of limits. So for polynomials, the limit of a polynomial is you just plug in the number. So nice and easy. Rational functions, assuming that you are not finding the limit where the denominator is 0, basically, as long as it's not the vertical asymptote, you can plug the numbers in. So if it's a vertical asymptote, you end up dividing by 0. So that's why you can't do it. That's where you kind of run into an issue here. But as long as whatever value you're interested in is not the vertical asymptote, you can plug in your number and find your limit that way. For radicals, it's really nice. You can just plug in your number. That's the nice thing about all of these, is that limits behave kind of as you would expect them to behave. You can just plug in your number and evaluate the function. And as long as you're not plugging in numbers that cause problems, you're okay. Like for the radical here, if it's an odd radical, an odd index, you can plug in any number you want. For even indexes, you need to make sure that it's a positive number, because when we have limits, we don't deal with imaginary numbers. So if you're trying to find the limit of like a square root and you're plugging in a negative, you can't do that. The key about limits is that limits exist for things that can be graphed and under the domain of what can be graphed. So imaginary numbers don't exist basically when you're looking at limits, because limits are things that they're for functions that you can graph. So if the part is not on the graph, then it's not part of the limit. You can take limits of composite functions. So we learned about function composition, where you plug one function into another. You can do the same thing with limits. What happens is you find the limit of the inside function, and then you take that answer and you plug it into the outside function. So you can do a composition of functions, and the limit always applies to the inside, and then the result of the limit goes on the outside. So those are all the properties. That's just basically, you're going to have a copy of this PowerPoint so you can have it for your reference. What I really want to show you is how these are used to find limits. And all of the ones that I'm doing today are ones that you can find limits of, that you're able to do with direct substitution, where you plug in your value, just to show you how these rules work. So we have the limit as x goes to 2 of 4x squared plus 3. So we're going to use our properties of limits to kind of break this down as small as it can get into its most basic pieces, find the limit of those pieces, and then kind of add them together to show how these work. So limits, if you have a limit of something that is added, you can split that apart as two separate limits added together. So the limit as x goes to 2 of 4x squared plus 3 is equal to the limit as x goes to 2 of 4x squared plus the limit as x goes to 2 of 3. So you can split, if you've got things that are added together, you can split that up into two separate limits. And when you're doing this, to have proper notation, you have to write the x goes to 2, all that underneath the limit. If you skip writing that part, then you're missing an important part of the notation. So that is basically the sum or difference rule property, that you can take a limit and kind of split it up. The next thing we can do is, there's any coefficients or any constants. So we've got a coefficient in front of our x squared. You can pull that out because that's multiplied. So we can rewrite this as 4 times the limit as x goes to 2 of x squared, and then plus the limit as x goes to 2 of 3. So any coefficients can be pulled out of the limit when they're multiplied. And then you kind of, you're just left with your variable part. So the limit of x squared, so the limit of any x to some exponent, we have a property, you can just plug in your value for x to find that limit. So you just basically, to evaluate the limit, you plug in 2 for x. So that's going to be 2 squared. And basically the same thing happens here with the limit of 3, except that there's no x to plug in. So it doesn't matter what x is, you're always going to get 3 here. So when you're showing your work, when you are actually plugging in your values for x, you are evaluating the limit. The limit notation disappears. So once you plug in those numbers, you need to make sure that your limit part is gone, because if you still write your limit there, then that is incorrect. You have taken the limit by plugging in the numbers. And then from there, it's just a matter of doing algebra. So we've got 4 times 2 squared, and 2 squared is 4. So it's 4 times 4 plus 3. 4 times 4 is 16 plus 3, and then that comes to 19. So our final answer, the limit here is 19. And this is the same thing you get if you, at the very beginning, instead of going through these steps, splitting it up, doing the x squared, pulling out the constant, if you plugged 2 in for x right away, you get 19. If you plug it into the 4x squared plus 3. So that's why we have this property about the polynomials, is that basically if you have a polynomial, you can just plug in that number and that is your limit. It follows from the other properties that we have, those other rules on this slide, that you've got a scalar multiple, the sum or difference, the power, those rules all follow. And that basically means that if you have any polynomial, you can just plug in your number to find the limit. So you wouldn't have to necessarily show every step that I've shown here. You can go straight to the third line where I have 4 times 2 squared plus 3. Any questions? Okay. So here's a rational function that we want to find the limit of. And you first need to make sure that the number you're finding the limit for does not make the denominator 0. If it does, then you need to do a different technique. So if I plug in 1 into the denominator, we get 2 in the denominator, so that's fine. So we don't have to worry about finding, making the denominator 0. So we're going to break down finding this limit using our properties. And in this case, you've got a fraction over a fraction, and you can take that limit and do the limit of the top over the limit of the bottom. So I've got the limit as x goes to 1 of x squared plus x plus 2 over x plus 1. And this is equal to the limit as x goes to 1 of the numerator, x squared plus x plus 2, divided by the limit as x goes to 1 of the denominator, x plus 1. So you can kind of think of like that limit notation in a way sort of distributes. It applies to the top and the bottom. So now that we've split this up, we have a polynomial on the top, we have a polynomial on the bottom, And we just found, or basically reinforced, that the limit of a polynomial means you just plug in the numbers. So to actually take the limit of x squared plus x plus 2, you're going to plug in 1 for x because we're interested in the limit as x goes to 1. So by taking that limit, once I plug in that value, the limit notation disappears. And then I'm going to do the same thing in the denominator. I have a polynomial x plus 1. I'm interested in the limit as x goes to 1, so you can replace x with 1. And so we end up with 1 squared plus 1 plus 2 over 1 plus 1. So that's 1 plus 1 plus 2. I got 4 on top, 2 in the denominator, and that comes out to 2. And so this is essentially equivalent to, you have a rational function, plug in x equals 1, whatever that number is, that is your limit. The questions. Okay. Here we want to find the limit as x goes to 0 of the square root of x squared plus 4. So what we have, if I go back to the property that we had, not a composite, with the radical, is that if you have x, but we have x squared plus 4, so we have more than one thing in the radical, so we can't necessarily use this property directly. We are actually going to do a composition function. We're going to do the function composition and combination with this radical function rule here. And I got a question for the previous. In this case, we can look at x approaches 1 is x equals 1. Yes. When you're taking limits, you can think of x approaches a number as x equals that number. And that will work if in that process you end up with undefined, then you have to do a different method. So if we ended up dividing by 0 in this case, then we can't plug that value in and you have to use a different method to find the limit. But as long as you're not getting a undefined, then you can just basically plug that in. So essentially that's what we're going to be doing here, is you can just plug in x equals 0 to find this limit, but I want to show you how the properties work that allow you to do that so that you understand why we're, what the rules are that allow us to do that. So this is going to be done with a function composition. So you're going to say what we have on our inside the square root, we're going to call that g of x. So we're going to say that g of x is equal to x squared plus 4. And then we're going to say f of x is the square root of x, basically the outside function. So function compositions, f of g of x basically means that you're plugging g of x into your f of x function. So our f of x is the square root of x. So we're plugging g of x into there. And so that gives us our x squared plus 4. So we have the square root of x squared plus 4, and we're breaking it apart. We're kind of moving from the right to the left so that we know what our g of x is and what our f of x is. So the rule for limits of function compositions, the limit as x goes to some number c of f of g of x is that you have f, and then inside f, you take the limit of g of x, and then you plug that into f, and then that will give you your answer essentially. So what we are going to do is we're going to find the limit of g of x. So we're going to actually do the limit as x squared plus 4. We're going to do that, get that answer, and then plug it into f. So we have the limit as x goes to 0 of f of g of x. So this is our square root of x squared plus 4. And we have f being the square root of x. So we're actually basically putting the square root part on the outside, and then inside we're going to find the limit as x goes to 0 of the x squared plus 4. So you can take that outside limit and kind of plug it into the inside of the function in order to evaluate it versus the limit of the whole thing. Now, the limit as x goes to 0 of x squared plus 4. So that is a polynomial. So that means we can just plug in for x, we can just plug in 0. So this is going to give us, we have the square root, and then when you take the limit of x squared plus 4, you're plugging in for x 0. So we get 0 squared plus 4 because we're interested in the limit as x goes to 0. So that will give us square root of 4. So because 0 squared, that's 0 plus 4. And then when we're evaluating here, we assume the positive answer because we're not solving. So when you're dealing with square roots, and you know you can have a plus or minus, it's when you're solving that you use a plus or a minus, but we are evaluating, we're not solving for x, so we use the positive. So the square root of 4 is equal to 2. And so the limit of this whole thing is equal to 2. So what basically the rule here, the fact that we have this function composition is that if you have the limit of a function inside of a function, you can basically put that limit part on the inside, go through your math, and then do the outside. There are questions?
Yes, I have a question.
Go ahead.
In the assignment, are we going to be required to show all these steps, or we know that we can just put that value in for x and we can move on?
You can just put the value in for x and move on. So you don't have to show like you wouldn't necessarily have to show this step right here. You can go like straight to here. But you do want to show that you plugged in that value and then show what that comes out to.
Okay, understand.
Mm-hmm. Other questions? Yes. Yeah, John, that's actually a very good point. So you said, you imagine that this is how a program would go about solving a problem like this. That's exactly right. So if you were a computer programmer and you were writing a program to do these kind of things, you wouldn't necessarily write it that just always plug in X. You would write it so that you could be like, okay, you've got this plugged inside of this, do this, go through that, and then plug it in the outside. It makes it much more general. And it actually reminds me, when I was in grad school, my my advisor had wrote a program on how to basically do derivatives, and just basically, wrote computer code to do calculus essentially. And it was using rules like this. It wasn't, you didn't have to code every single possible function you might see. You code the basic ones, and then you code the properties, and you use those properties to break everything down into those basic functions. And then you can basically take the derivative of anything, because instead of looking at every possible combination of equation you can get, you're breaking it all down to the very basics of working with that. So yeah, it adds versatility. It seems kind of, when you're trying to code it, it's very abstract, because you're doing things like put the limit inside the limit and stuff like that. But it allows you to write code that handles any type of problem, not just the ones that you coded for. So that is a really good point. And for anybody that says, well, why do I have to take this class and who might be doing programming? Well, this is where understanding these rules can really come into handy when you're coding. It, may be harder initially writing the code, but then once it's done, it's done. You don't have to make any fixes. So I've got a couple more, and these are going to be trig ones. So especially because, I know you guys absolutely love trig, which I don't think anybody actually said they loved trig after going through that week. So we have the limit as x goes to pi of x times the cosine of x. So this is where knowing the rules really helps, because with those polynomials, it seems easy enough. Just kind of, plug in the number. You can kind of understand what's going on. But once you start doing trig functions, it's like, wait, it's like it's just bizarre. So we're going to use the rules. We're going to think of this. So we've got the limit as x goes to pi of x times the cosine of x. And we're going to split this up, because we basically got x times cosine x. And so we've got two different functions. So we're going to split this up as the limit of x times the limit of cosine of x. So the limit as x goes to pi of x times the limit as x goes to pi of cosine of x. So the limit as x goes to pi, you just plug in pi, and that's basically just going to give you pi. So you're going to have pi in front there. And then when you plug in pi here into cosine of x, you're going to get cosine of pi. So now you have to kind of go back to your unit circle, and you're like, well, what is the cosine of pi? If you don't have it memorized, if you have like a cheat sheet somewhere where you have these common angles, that will be really important. I always go back to my unit circle. And so I know on the unit circle that pi is going to be that angle where my ordered pair is -1, 0. And cosine is always the x value. So I know that the cosine of pi is equal to -1. So I always go back to my unit circle there. So the limit of this is going to be pi times -1, or negative pi. So you can basically find the limit of x, find the limit of cosine, and multiply those together. And you can basically, plug in pi from the very beginning, get pi times cosine pi. It will come out to the same thing. Other questions? And whenever you're doing limits with trig functions, it's always in radians. So yes, pi is in it. Yes, always. If you see pi, always radians. Whenever you're doing trig and it's doing stuff with limits or in calculus, basically anytime you see trig in math, assume you are in radians unless otherwise specified. So I never put my calculator in degree mode. I will do everything in radians and then as needed convert to degrees. Or if I'm given degrees, I convert to radians first and then do all my stuff in radians. So this is actually really important on the first homework problem because that it specifies X is in radians. So even though we're not given, like, you're not plugging in numbers like pi, you're plugging in numbers for X, but we always do radians. So if your calculator is in the wrong mode, then your table for number one is going to be completely incorrect because you're in the wrong mode because it's radians, not degrees. So here's another one. This is the last example that I have. We've got the limit as X goes to 0 of sine squared X. So this is another one where we're kind of doing the function composition. So we've got the limit as X goes to 0. And again, assume this is radians, 0 radians, which is the same as 0 degrees. So I guess in that case, it doesn't really matter. But sine squared X, that is equal to the limit as X goes to 0 of sine of X squared. So sine squared is sine of X squared. Now, when we're taking the limit of here, this is basically our function composition. So you can rewrite this as taking the limit as X goes to 0 of sine of X, and then squaring your answer there. So you can basically take that limit, put it on the inside, find that value, and then square it. So for trig functions, when we're finding that limit, you just plug in your number. So this is going to be equal to the sine of 0 when we plug in our value squared. So now I'm going back to my unit circle. So 0 angle would put me right here at the ordered pair 1, 0. And sine is always the y value. So the y value of 1, 0 is 0. So sine of 0 is equal to 0. So this is actually equal to 0 squared, which is just 0. So the limit as X goes to 0 of sine squared of X is equal to 0. And basically you could just plug in your value for X, find sine squared of X, though calculators don't have sine squared on their calculator. So you would have to know that sine squared of X is sine of X squared. So you would still basically have to do what I did here, find the sine first and then square it. But as long as you're not getting a value of undefined, you're okay. Like if we had tangent, I believe the tangent of 0 is it tangent or cotangent? I always get confused. I think it's cotangent of 0 is undefined. Let me. Yeah. So if we were doing like cotangent as X goes to 0, you would get a value of undefined because the cotangent of 0 is undefined. And so this method wouldn't work. You'd have to find some other way to determine what your limit was. But we're not, we're plugging in these values. We're not getting any problems with undefined or error or anything like that. So we can just kind of apply these rules, show the steps, and that's how you find your limit. Are there any questions? Yes, these methods are easier than the graphing method. I recommend doing this method, and then if this method doesn't work, then going to graphing. So I will tell you flat out, number 5, you can't use this method because, well, because number 5, it's asking you to reach to infinity. You can't plug infinity in. Infinity is not a number. So like anytime you have X going to infinity or negative infinity, you can't use this method because you can't actually plug those numbers in. So you could do those by graphing, or you have to kind of do it by understanding what the limit means, or there's some other tricks that you can do. There are some properties when limits go to infinity that that you learn. And I do have a video where I kind of mentioned some of those, but we never actually plug in infinity for x because it's not a number that you can plug in. Any other questions or comments?
Are we gonna go over any of the graphing at all?
Not in this video, no.
Okay.
I do have a
in
video
general-
that goes over it.
In general, but my answer, so if I'm looking for, as X approaches something, my answer is looking for on the Y. Is that correct?
Yes, yeah. I could open up Desmos and I can graph these and we can like verify our answers. So like the one we just did, sine squared of x. So you would have your graph sine squared of x, which looks like this. And then we were wondering was x goes to 0. So that's saying as x is approaching 0 from the left and the right, where is the y value? And so you can see that the y value is 0. So that's why we got a value of 0 when we went through the algebra, basically, is it's the y value at that point. So let me find another one. We'll plug in this one. X times cosine of x is x goes to pi. So our function is x times cosine of x. It looks like this, very interesting. And we want to know what happens as x goes to pi, which is 3.14. So I'm just going to kind of, this is 3. So somewhere around here, there we go. Okay, 3.14, pi is 3.141592 something. But you can see that at approximately pi, our y value is negative pi, which matches what we got with the algebra. Oh, I moved my mouse and now I'm no longer on the number. There we go. So the y value is, when you're finding the limit, it's basically asking what is the y value. And what makes it powerful is that it allows you to find y values for things that may not actually have a number at that point. Like if there's asymptotes or gaps or things like that. So, and John mentioned making a chart. So Desmos has this thing with a table, which is really nice. And you can use that to kind of make a table of values and kind of see what happens when y is approaching. Like here, we want to approach pi. So I think I can, if I remember how I did this. So I can say that I'm using x1. So any of my input value here for x1, I can put my function value here as my x. And then let's say the point of, we're interested in pi, when we're approaching pi. So I can just call that C. So I usually, the way that I do this is I have like C minus 0.1, C minus 0.01, C minus 0.001, C plus 0.001, 0.01. Like you want to kind of get close to your values when you're making a table of values. And so you're interested in what is happening at C, but you kind of want to see what happens nearby there in case it's like it has a vertical asymptote. And so you can see that the numbers as we approach C from either side, they do approach pi. It's not exactly pi, but it's close to pi. And so this is a method that you would use if you had an asymptote, like if you had a vertical asymptote. So let's say we're going to just make up a function here, 1 over x plus 1. Oh yeah, I gotta have to. So that has a vertical asymptote at -1. So we can't just plug in -1 for x because it's undefined. but we can make a table of values to kind of figure out what the limit is, which in this case, the left side, you want to have the left side and the right side going to the same number. And in this case, they are not going to the same number, so the limit would not exist in this case. And I graph what that is. So at x -1, there are two sides of the graph are going to two different parts. One's going to positive infinity, one's going to negative infinity. They have to match in order for the limit to exist. So the limit at this point does not exist. And then the table kind of reinforces that. But this is an example of one that you can't do algebraically because you can't actually plug in -1 for x. So you would have to do it one of these other methods. Any other questions or comments? Yes. So the question that says the famous number that the thing approaches, it's not pi, as pi is 3.14. The number approaches Euler's number, which is 2.71 something. So that is E, the other famous number. Yes, if you got a 1000 on there, then double check how you put it in your calculator. So yeah, you should be getting numbers for number 2. Your values should all be 2 point something. So if you're not getting that when you're plugging in numbers, and you want to be plugging numbers close to 0, so they're going to be very small numbers. So if you're not getting those numbers, then you might have, put in your calculator wrong. So you might want to double check that your parentheses are in the right place and all that sort of thing. Questions 3 and 4, you only need to use the graph. Yeah, if you don't use the parentheses, that will definitely get it wrong. So the parentheses are very important. Yeah, 3 and 4, you don't need to write an equation or anything like that. You only need to look at the graph, so you don't have to come up with what those are. And then number 5 is one where it's going to infinity. So you have to kind of think about the graph and look at it on that aspect.